Hi guys. Um, Today I want to talk about the reduced impedance effect. This is part of the asymmetrical regauging and stuff that we've covered for some time now. I just want to point out some almost sort of simple things that maybe even sort of possibly a little bit easy to overlook by many people. The reduced impedance effect is an effect where if you're able to stop or nullify the change in magnetic field, creating a back EMF, you can actually cause an effect where the changing magnetic field within a coil can change very, very much faster than what it would normally change if it didn't have a back EMF. And what that basically means, an analogy would be put an electric motor on the bench and then spin it up with, say, 10 volts DC or something like that. It'll start off going slow and then it'll speed up, speed up, speed up, speed up. Now, as it starts off going slow, the current draw will be very high. As the motor speeds up, the current draw will reduce. So what it's doing is the current is actually coming down as the motor spins faster. Okay, and that's the back EMF in the coils. The back EMF basically is creating a larger resistance in the coils because the magnetic field is changing faster within the coils, which essentially creates a larger resistance. The resistance is measured in ohms, but the inductive reactance is what causes the resistance. Now, at resonance, capacitive reactance and inductive reactance are equal, and they therefore cancel each other out. They're still there, but they cancel each other out. They still have a value, but they're equal. So the impedance, which consists of the XC and XL, the impedance is measured in ohms. So you'd normally see a number in a similar format to this. So over here would be your DC resistance of the coil, and then over here would be what they call the AC resistance of the coil. The J plus or J minus just means whether it's capacitive leading or reactance, inductance leading. Inductance leading for plus and capacitive leading for negative. Okay, so inside the coil, as the magnetic field changes very fast and increases in the frequency that it changes, the back EMF in the coil opposes the forward EMF. So basically what it's doing is it's creating a higher resistance in the coil. Now, if you can change the resistance in the coil, and remember what I'm talking about is the impedance, not the resistance as such. So it's the reactance, how the coil can react to the current changing. How that works is basically if it's opposing, if there's a high opposing back EMF, then the coil itself will have a high reactance, which is the impedance. Now, if you're able to somehow nullify the impedance part of the DC ohms, if you're able to nullify the inductive reactance and capacitive reactance, if you're able to get them to a point where the back EMF is either non-existent or helps you in an assistive way, then the coil can react very much faster to changing magnetic fields. And I show that experiment here. We'll have a quick look. This is my original, or one of my original PDFs. Very, very old now, about 3 or 4 years old, roughly. Now, this is the experiment here. So the flow of current in a wire when there is no magnetic field. Okay, this experiment 1, this is inductive, this coil, it's in parallel, series I should say. And obviously we can see a very small time base, 50 milliseconds, but the current is ramping up over almost 100 millisecond time base. It's about 90 or something like that. And if we make the coil non-inductive, move to a non-inductive mode on a even smaller time base, we have a much, much, much faster change by many orders of magnitude, faster so the current going through the coil can ramp right up to a maximum value in about 500 microseconds. So you can see much faster. So the reduced impedance effect, I'll just let you know that this has not really been covered anywhere else on the internet as far as I'm aware. This is new. This is something that you won't find anywhere else. This is our material. I have shared it with you. No one else has gone through this sort of stuff in this detail. So this is aboveudemy.com material. This is no one else's. However, impedance and all that stuff is well known. It's been around forever. So anyway, the format that you'll find, okay, this is the format of the impedance. Okay, so DC resistance here. DC resistance of the coil is not going to change. The number that will change is the reactance, okay, inductive reactance. Plus J means it's, down here it means it's inductive leading, not capacitive. Capacitive is negative, okay. So the impedance is measured in ohms, and as the impedance changes in the coil, then with the motor scenario, if the motor speeds up, then the input current drops down. So it's sort of in reverse. You've got to think reverse. So the faster the motor's going, the lower the current's going to draw from the source. And the slower the current's, the slower the motor's going, the higher the current's going to be drawn from the source. Okay, so it's the change in time rate of change of the magnetic field within the coil that creates the back EMF. Okay, and it's reasonably well known about the motor scenario. Most people know about it, but no one really has investigated how to cancel it. Okay, so I've gone through here, detailed the experiment. Okay, again, showing the 50 milliseconds. Okay, so 50 from there to there, so that's one division is 50, and you can work the rest out. So it's about 90 or so milliseconds all up. Okay, and that's inductive. So when the coil is highly inductive, it's a very slow change in magnetic field. And when the coil is non-inductive, okay, so when the currents are opposing, which you can think of currents opposing, then there's a very fast change in magnetic field, and it's by many orders of magnitude. So we're looking at difference between 50 milliseconds, 500 milliseconds, and you can work out the difference between the time base here. So from there to there, 500 milliseconds is from there to there. So we're looking about in between maybe 600 and 700 microseconds. Okay, so a very important concept, a concept that everybody needs to know to be able to understand how these coils are working. Okay, this is really important stuff. Always look for the arrows. The arrows are really important. Moving on, I want to again show you the arrows. Okay, this is the MEG team data that they shared. I have changed this just for illustration purposes. So what all I've done is flip this bottom trace vertically. So it was vertically this way, modified, and this is the way you should really see it. Okay, so it should be this way up and not the other way up. All right, so what we've got to think about is from the green arrow here, okay, that's the start of a cycle. So green arrow, and if you look up on the input starts. So the input is on when the output's on. Okay, the output ramps up as the input ramps up. Okay, if we were to draw a line all the way down here, you'll see that the input is at its peak well before the output's at its peak, which is the red arrow. Okay, so the input is switched off, and if you sort of draw a line down again, the switch off point is slightly before the peak of the output. So what we can say is from the green arrow to the red arrow is a ramp up in magnetic fields. Now you've got to remember we've got two magnetic fields here. where we've got two magnetic fields opposing. And why is this such a short time? Why is from the green arrow to the red arrow, why is it such a short time? Roughly around about the 10% duty cycle. Why is it such a short time? Is because of the reduced impedance effect. Okay, what's happening here is the two output coils have such a low impedance that their magnetic fields can ramp up very, very, very fast. Okay, they can get to peak value very fast. And as our input is being assisted by one of the magnetic fields, okay, so we've got three magnetic fields in all. Okay, we've got the input magnetic field, and then we've got the output magnetic field which opposes the input, and then we've got a magnetic field, the third output, or the second output coil, but third magnetic field, which assists the input. So it's 1 plus 1 plus negative 1 equals 1. Okay, probably should have been the other way around. 1 plus negative 1 plus 1 equals 1. So we have a greater magnetic field in the forward direction, okay, from the green arrow to the red arrow. And because our coils are opposing, we have a very, very low impedance in the coils. We're just talking about DC resistance, which can be very low, in the order of probably in some coils less than an ohm of DC resistance. Okay, and then our input coil switched off. And this is a very important thing here. When it's switched off at the red arrow, or just before the red arrow, this changes entirely the magnetic fields. And remembering that inductance is how the current traverses through the coil. So from the green arrow to the blue arrow, we have a complete change in inductance between the coils. The coil's inductance changes completely. So we have a very low inductance here because the magnetic fields are opposing. We've essentially cancelled the back EMF because we have a third magnetic field in the opposite direction. The coil's inductance has become almost zero. And because of that, we can crank it up very, very fast and get a very high magnetic field very, very quickly, which in one of the magnetic fields assists our input. So it's in the positive direction. Then when our input is switched off, just before the red arrow, okay, so you've got to remember we're dropping back to two magnetic fields now, not three, because our input's off. When we drop back to two magnetic fields, okay, our output becomes a linear decay of energy generation. So this is a collapsing magnetic field between the two coils, peak magnetic field up here. And remembering this is voltage, not current. So what we've got to do is we've essentially got to think that because we've got a resistive load on the output, the voltage and current are almost in phase, almost 0 degrees from each other. There's no phase angle difference, and the coil itself has a current which would almost look the same. Okay, so again, this is a voltage trace, but the voltage trace will be very, very similar, if not the same, to the current trace because it's pure power. Pure power is DC output, basically. Okay, so this linear decay here of the output, okay, is the magnetic field collapsing from peak magnetic field because they've squeezed. We've got two magnetic fields opposing all the way up to the red arrow. Then we drop our input switched off, and then it collapses, okay, from peak magnetic field all the way down. So this is a sawtooth wave. It's asymmetrical in nature because we have changed induction from this point here back. Okay, so the inductance or inductance, which is a function of the current through the coil, LDI dt, I think it is, from memory, the function has changed. Okay, our coils have changed, the geometry has changed. We now have a generation period down here as well as over here. Okay, so this is all output, and it's all output to the load. So because our coils oppose one in the forward direction, two in the forward direction, one in the back direction. Okay, so from here to here would be one cycle. Okay, input is considered so positive here gives us a positive peak down to here. So our output is nearly 100% duty cycle, only having very, very small off times at the bottoms of the peaks there. Alright, so I hope this is making a bit more sense. Asymmetrical regauging, got to remember we have output on all the time. Output all the time. Okay, so throughout the whole cycle. There's no, some of the stuff I've shown in the past where we're sort of showing the magnetic fields interacting with each other. We've shown two different parts of the cycle and showing what they do at different parts of the cycle to try and get people to understand, you know, the transforming effect, or at least the generation effect. This is the same effect, but essentially we're using both parts of the cycle. This is, I forget exactly, but I think it's 31 kilohertz, which would be a full cycle from there to there, and a 10% duty cycle roughly of input at the start. Each sawtooth waveform asymmetrical because we're having a difference in the magnetic fields of the coils again. Okay, so LDI/dt is changing because of our input. Okay, so again, input plus one output coil in the forward direction, one output coil in the negative direction. Now the one output coil in the negative direction is Lenz's law, and the output coil in the forward direction is Lenz's law again, but from the secondary coil, not from the primary coil. Okay, hope that makes some sense. So back to reduced impedance effect. Now, with mutual inductance with another coil over here, we can nullify some of these fields, and that's basically the idea behind the drawing that I've shared with people for so long. Yeah, so this is the coils I've been showing for quite some time. And again, I've covered this in one of the previous videos, or a couple now. You can see there's a difference in coupling coefficient between this coil, the first secondary coil, and the primary coil. So the primary coil needs to induce a current in this coil. The primary magnetic field would be this arrow, but in reverse. The magnetic field from the first secondary coil would be this arrow. And then the trick is that we have to get this coil over here to produce a magnetic field in the opposing direction, which would be assistive to the input coil. The input coil, remembering that there'd be this arrow but in reverse. So this arrow here would be in the same direction as the magnetic field from the primary coil. So again, this coil over here assists the magnetic field from the input coil, the green coil, but does oppose the magnetic field from this coil over here. Okay, so we have three magnetic fields. It's an asymmetrical device. I've tried to sort of cover this in quite a few different posts. I've tried to make it as understandable as possible. It's very hard because you're sort of explaining something that's quite different, and people may not necessarily understand the difference. But you can see here, if we were to have a pulley at the top of a hill, the mass over here, M2, would be a combination of the primary coil and the secondary output coil. The secondary output coil, okay, the mass is larger, it's on a larger slope, so it's only pulling a very small mass up the hill, so the small mass is going to get pulled up the hill while the large mass gets pulled down the hill by gravity, obviously. And you've got to remember that sawtooth wave, which we're looking at here, the sawtooth wave has the same effect. Okay, you've got to remember it's asymmetrical, so where there's a heavier load, there's going to be less distance that needs to be traveled, okay, which is sort of what I've tried to say down here. So input frequency and duty cycle tuned for magnetic resonance. And that's important. Magnetic resonance is important. Hopefully soon we'll cover stuff with this. I have a bit of a time frame I have planned out, but I may bring that timeline ahead a little bit because we're doing so well on the forum at the moment. Anyway, secondary coil 1 conducts current, powers the load. Okay, so secondary coil 2 is in opposition to 1. Okay, Lenz's law. So we're going to have opposing, opposing magnetic fields. It gets a bit complicated because we're sort of dealing with magnetic fields that, like the Mr. Prever experiment, one's in reverse, and we need to start thinking that way. Anyway, the secondary coil 2 is switched in. So by switching it in such a way, getting the timing of the switch in such a way that we can get this to happen. Okay, so we have a magnetic field which is assisting the input. So 1 magnetic field up the hill, 2 magnetic fields down the hill. If we were to flip this over, then we'd have the same as the picture that we looked at just a minute ago. Or equivalently, we're looking at 1 plus -1 plus 1 equals 1. Or if we want to look at the arrows, we've got 1 forward, 1 back, and then 1 forward again. Okay, so this is representing the MMF, which is the magnemotive force, which ends up being the currents in the coils. And as I've covered here somewhere, the magnemotive force is current through turns, which is the ampere turns, which is equivalent to the magnetic field in Weber's or Orsted's, I think it is, off the top of my head, brain blank there. And it's directional, comes in a vector form. So we've got to think magnetic field vectors, and the generation of energy requires this to happen. So again, coming back to what we talked about some time ago, when you're generating energy, the current has to be supported. Otherwise, if we generate an EMF and the current's not supported, if there's no opposition of current between source and destination, then we have a large voltage spike, which doesn't really give us a huge amount of current. It's mostly just voltage, and basically what happens is it all collapses very fast and we have no real pumping of energy. And remembering our triangle, which is the pumping of energy. I'll show you that now. Okay, so this is our triangle, our pumping of energy. So when we have a large potential, okay, large voltage, then if we were to drop 2 magnetic fields together, and a good analogy for this is dropping the magnetic, the neodymium magnet through the copper tube. If we drop it down, we're going to see a linear decay of the magnet over time. Okay, so for every millimeter the magnet falls, it's going to be a linear decay over time, and that's why it's a straight line here, and that's why we see a straight line on the magnetic fields as well. Let's pop back to the image we just looked at before. Okay, so this is the linear decay over time, and remembering that this stage here, there's only 2 output coils which are opposing each other, and this is pumping. This is pumping current. So this is the same linear decay over time when you look at the magnet falling through a closed copper tube. It goes very, very much slower. Okay, it falls at a linear rate through the tube, and then when there's no magnetic fields that oppose the magnet, then it falls at terminal velocity again. Okay, so remembering again what we talked about, magnetic fields pump all the way up to the top. So these are 2 magnetic fields opposing each other on the output coils. The input coil is assisted by, so input here is assisted by 1 output coil, and then opposed by the other output coil. Okay, so we have a reduced impedance effect all the way up to here. So we can get a very, very fast increase in amplitude all the way to the top. Okay, and if we have low resistance coils, this time would reduce even further. So you need to find this time. This is something that takes a little bit of adjusting, takes a little bit of fiddling, takes a huge amount of understanding. It took me years to understand the basics here. I was fiddling and fiddling and fiddling for years before I grasped any of this. Very difficult. And anyway, up until here, the red arrow is switch off, no input anymore. Okay, so and remembering that this period here is a different inductance between the coils as this period over here. So inductance changes from green arrow to blue arrow. Linear decay over time of the magnetic fields decaying from peak all the way down. So this whole from green arrow to blue arrow is a energy generation, if you want to call it generation. I don't like the term generation. And energy pumping, okay, because this is a pump. We're pumping energy from green arrow to blue arrow, and this is all done magnetic resonance. So the magnetic fields need to change at a resonant, if you like, frequency in between the red arrow and green arrow. You need to find this resonance of your coils to make this happen. And again, to make one coil assist your input, there needs to be a delayed conduction. So something that will actually make the secondary coil assist your input. Okay. Otherwise, there's going to be no assistive force. Both coils, if they have conduction full period here, will basically oppose your input. You'll end up with an input opposed by both output coils if there's no delay in conduction, or at least delay in magnetic field or mutual inductance between the two coils. So again, the trick is to get one of your output coils assist your input. And when one of your output coils is assisting your input, then this all comes to life. This is a magnetic pump in the same way as the hydraulic ram pump. All it requires is a flow of water, which water flows downhill thanks very much to gravity, and a gravity-fed water pump will pump all day long as long as there's no part failure in the hydraulic ram pump. We've shown that for years and years and years now. So it's a asymmetrical system. You've got to have asymmetrical system, otherwise there won't be any gain in energy. It'll be what comes in, comes out, which essentially is just a standard transformer or a generator. And what people need to realize is that the same processes exist between a transformer and a generator. Okay, the only difference is that the input energy to a generator is via the shaft. Now, shaft is torque, which is back to Newton's laws, which we covered in a post earlier on as well. In a transformer, the torque comes in the form of current, and the current coming into the input coil it goes up as the resistance comes down. So as we load the secondary coil, we have a reverse effect to what we're seeing here. And essentially the inductance or the current through the coil change as the magnetic field changes in a transformer. So the magnetic field is current, again through turns, which is Weber's or Oersted's. I think there's another term as well for it. I can't remember off the top of my head. But anyway, the current is the torque in a transformer, and the current will go up as the load increases on the transformer, which is the same as the torque on the shaft in the generator. Okay, so it's the same deal. Both devices use induction, electromagnetic induction. They're both exactly the same processes. There's no difference, but the difference is in the form of work, which is input. Again, current to a transformer is the work, and the shaft torque, which is the force, rotational force on the shaft, in the form of torque to a generator. It's the only difference in work. All right, so I'm going to try and keep this video short. If this video helped you, if this video was any use, I would like to ask for a, if you could, just a small donation. Again, we are changing the world. We are making a big difference. Our energy forum is unique. We have information on our forum that is nowhere else in the world. And we have fantastic people all helping us out. So I'd like to thank everybody that donates either time or money to the forum. Thank you, everybody. We've got a fantastic bunch of people, and if you can, help out the members that share their work as well, because it's very important that we keep supporting the good people that do great work and share it with everybody online. Very important stuff. If we can keep the people working, that get paid for their time, their effort, their materials and all that sort of thing, then this whole process will go so much faster. Thank you again.